Sadly, I couldn't join you guys in South Africa today, but I still have the privilege to present to you the practical aspects of Technetium-99m. I hope you can find something in this that you didn't know before or that you find interesting. So thank you for your kind attention. So we will discuss the factors that influences radio labeling, which include aluminum contamination, the ratio of the technetium element versus the stannous chloride or reducing agent in your mixture, the effect of radiolysis, and also following your radio labeling protocol wisely. First plugin of the presentation, and there will be some more coming, is to follow my YouTube channel. I give weekly lectures for MH students, so please spread it around. Also small basic radiopharmacy snacks, just the basic principles. Indeed, I also go a bit more deeper in the technetium chemistry. Also some more advanced topics like lutetium labeling, actinium, and also you can contact me and request a lecture that you would like to have. Please support me. The second plugin is to first maybe consult the presentation presented earlier by Sandile about molybdenum generators. This will also be available online, the recording afterwards, so that you understand the principles of handling your generator, because the source of your technetium is also a really important principle that influences your radio labeling and how that works. So the two cannot be done without one another, which is so nice that Sandile already presented the topic earlier. So just a quick refresh of factors that really influences radio labeling is, and the yield from the generator is the presence of ethanol. So both the labeling products and as well as the generator does not like the presence of ethanol. So although we need to really maintain sterility, and this is very useful, you should allow all of your septums that you have swiped with ethanol to dry first before you attempt any radio labeling procedure or elution. Eluate quality control is really important, as Sandile discussed before. So any of these problems in your eluate is a failure, and you should not try to continue to radio label. So if there is some molybdenum breakthrough, some aluminium breakthrough, you will see that this will really influence your radio labeling later on. And it's of course not safe for the patient eventually to use. So any of these, you cannot go on with your labeling. But say you have a good eluate and you can continue with your labeling, then there is some factors that you have to look after to be able to radio label perfectly. So, first one is alumina breakthrough. The newer generators are designed with smaller columns, so this is not really an issue anymore. But in the past, it was quite a difficult thing. So still, you have to monitor your first eluate that you receive from your generator for alumina. The presence of alumina can result in all different types of interactions with radiopharmaceuticals. And just as an example, if there is some alumina present in your eluate when you label NDP, it will form colloids and localize in the liver, for instance. If you label DTPA for GFR measurements, the presence of alumina will influence the radio labeling and result in free pertechnetate and then an inaccurate GFR determination. You will of course not realize this. If you have unlabeled pertechnetate that is contaminated with alumina and you inject it into your patient, you will not have the proper thyroid uptake. It will be decreased. And then colloidal preparations will make bigger particles, and this can even cause embolism, which is quite dangerous. So alumina breakthrough is really important to monitor. Then the next one we go to is the ratio of technetium element versus stannous chloride. So this graph I really like. It has been a combination of many people before me that presented, and I made this graph in the end. Influenced by a lot of my mentors that I will thank in the end. So the cold kit contents have tin in, which is reducing the technetium to a state where it's chemically active, and then the technetium can react with your ligand, your MDP or your pyrophosphate or whatever you are labeling. But if you have too little tin compared to your concentration of the technetium element, you will have a problem with labeling and your protecnitate will not be reduced. Also, if you have too much technetium compared, so too little tin, yes, but too much technetium as well, and also the influence of ground state technetium. So, what is ground state technetium? When you receive your eluate, you will see or your generator, your first elution will be contaminated with technetium-99 because it has been eluted even 2 days before or even 3 days. So any generator eluted not within 24 hours is a problem with the ingrowth of technetium-99. So on your column, your molybdenum-99 decay with a half-life of 66 hours to technetium-99m, but then 6 hours decay half-life forms technetium-99. So technetium-99 will continue building up and up and up, whereas your molybdenum, of course, goes down over time with the 66 hours half-life, and your technetium kind of stays relatively stable. So why is this a problem? Technetium-99 is the same chemical as technetium-99m, even though their radioactive properties differ. So they will still be incorporated in your molecule. For instance, here is system B with ground state technetium, which you cannot measure with our radioactive equipment, and then the technetium-99m that you want. So all your ligand and your reducing agent that's necessary to make your radiopharmaceutical will be used up by the non-radioactive technetium-99, relatively non-radioactive technetium-99, and then your technetium-99m will not be incorporated and it will form protecnitate, leading to a low radiolabeling yield. So you get the non-imaging technetium-99 instead of the technetium-99m system maybe that you wanted. This is because your technetium concentration is more than what your stannous chloride can handle. This technetium is made up of the radioactive 99m as well as the ground state 99. In this case, the age of the eluate as well as the time elapsed since the previous elution becomes problematic. Because if you have a fresh eluate and it stands on the shelf, it also builds up technetium-99 over time. So, if you have a generator that hasn't been, the worst case scenario would be a generator that hasn't been eluted after the weekend, and it has stand for 72 hours, and you elute it, and then you let your eluate also stand for 6 hours, and then you have really very little technetium-99m to speak of. Same problems occur in generators that are older with time. So that is one way you can have more technetium than your stannous chloride. That is in your formulation or in your kit. Another one that is a big problem is that you should not be bashing kits. You should not be adding more protecnitate than what is prescribed on the package insert. This results in unreacted free protecnitate and a low radiochemical yield. Okay, please don't do this. Then, of course, fractionation of cold kits is also something that is being done quite regularly in practice, especially with kits that you do not use every day. This is also a problem because you have your stannous chloride degrades at a solution. So even if you put it in the freezer, you defrost it, it has been in solution. You're introducing oxygen that will take away some of your stannous chloride as well, reduce that as well, and this influences all of these aspects. So this reduces the shelf life of your cold kit, and it definitely reduces the radiochemical yield that you will get in the end. Yeah. These are all the problems that are caused by the splitting of kits. So with no good conscience can I say that splitting of kits is good practice, and I strongly discourage you to do this. It can lead to too little tin in the kit due to degradation or decomposition due to air, or just the fact that you will add maybe more technetium in the end when you make up these kits. It can have problems with the stability of the ligand. You can have water being added during this process, and it actually influences all the properties that make up the stability of the radiopharmaceutical. So it can influence radiolabeling yield, radiolabeling purity, and also the stability of the final compound. And then my next plugin would be for the discussion by Samantha later this on Friday, the 25th of August, where the different operational levels in the radiopharmacy are discussed, as well as who has the authority to do these kinds of procedures. And note that modification of existing commercial kits, and this includes the bashing and the splitting, is actually operational level 3, which is already a very high operational level. And as she will tell you in her presentation, you need extra equipment to be able to do it, a cleaner environment, and most often also a chemist or a radiopharmacist involved. So even if you have been doing this for years, it is discouraged, and there is a lot more technicalities to it, and it should be considered as not good practice. So, what kits are most sensitive to the amount of technetium and the stannous chloride or reducing agent? So this is to make it more practical for you. When you stand in the radiopharmacy, you have an older eluate, you do receive your generator over the weekend, and on Monday you absolutely have to do some procedures without eluting before. What kits could you possibly try to label, and which ones should you not? And this is going to make sense for you based on the practice that you have done in the past. So kits more sensitive to this technetium stannous chloride ratio are HMPAO, MAG3, Hynek PSMA, and Sestamib. So in the past, you had most problems for sure with one of these radiopharmaceuticals, and this is because these kits are really sensitive to the ratio of technetium and stannous chloride. So if you are coming in on a Monday and you need to radio label, you can definitely try MDP and pyrophosphate, as well as protectate and colloidal technetium. Maybe due to the type of examinations that you do with DTPA, you would want to be a bit more careful because you really need to have a stable DTPA. But then again, you do your ITLC and you make sure that you've radio labeled well, and then you can continue. Kits that you will struggle with is HMPAO, as you all know, MAG3 and Hynek PSMA and Sestamib. So it's better to leave these to the Tuesday, where you have still a fresh generator that's giving you a high activity, and it has been eluted in the last 24 hours. Even going further, it might be even advised to take a second eluate of the day, say at 10 o'clock, and elute again, and then label these kits with that elution. This will save you a lot of hassle. And literature indeed conforms with what I've said. I had looked at this article, which is really nice, and it indicated the kits that has been giving problems at this particular institution, and it has been MAG3, HMPAO, and maybe. So the chemistry also speaks to the real life situation, and now we know why it is giving these issues. The next point I want to talk about is radiolysis. Radiolysis is the breakdown of the radiopharmaceutical due to irradiation. So if you have a high concentration of activity in your protecnitate solution, it can sometimes form ions, free radicals, or peroxides that can attack the radiopharmaceutical, make it unstable, and then also reduces the radiochemical purity. It also increases, like I said, with increased activity concentrations, and again, those kits that always give a problem is also sensitive to with these radiolysis problems. So if you have a kit, and this also builds up over time, so if you have an older eluate, not only will the ground state technetium have a problem here, but also the radiolysis and the free radicals and peroxide that has been building up in this mixture. Sometimes these also take place in your generator, and this can also influence your elution yield. The Other problem that you can have is when you don't adhere to the radio labeling protocol. And here I'm going to take MAC3 as an example. So it's one of the more tricky ones, and I thought this is just to show you how every step is actually tied into the chemistry and how it's important to follow this. So if it says heat up for 10 minutes at 100 degrees, please heat it up for 10 minutes at 100 degrees. And if it says cool down for 15 minutes, do that, because each of these steps have been designed to result in the end radiopharmaceutical. So MAC3 is always packaged in a protected version. So this benzoyl group here protects the sulfur group during storage to increase the shelf life. So when you start radio labeling, you will add protecnitate. Intermediate ligand tartrate will be formed during this process. So your tin in the mixture reduces your protecnitate. The reduced protecnitate reacts with your tartrate, and this forms your intermediate technetium tartrate. This is a weak ligand, so it can always be exchanged with something else in the future, which is where the next steps come in. Now that you've had your intermediate form, it's important for only MAC3 to remove the excess stannous ions. That is why this is one of the only radiopharmaceutical kits where you would introduce air. So after the mixture, you are inducing a milliliter of air, and this is to take away all the excess stannous ions. In your other radiopharmaceutical kits, you would normally not introduce air because the excess stannous ions is actually there to keep it stable and make the formulation stable over a longer time. So for instance, HMPAO, never introduce air. Now the kit asks, MAC3 asks that you heat it up for 10 minutes, and this removes this deep protective group. Now that the tartrate is formed, the tin is removed, we are ready to deprotect the ligand by heating it, and also this heating up causes the MAC3 to dissolve. Only when it cools down, the Technetium-99m leaves the weaker tartrate ligand and it's getting exchanged into the MAC3, and this process takes 15 minutes to be complete and have a high radiochemical yield of your Technetium MAC3. So you see, if any of these steps are not done, you will end up having poor radio labeling yield, and that's why you should follow it to the letter. Now I'm going to give you some practical examples, and I'm sure some of these you will also have experienced in the past, and it might make a bit more sense. So, common problems with technetium MDP. Why can this go wrong? If you have alumina breakthrough and you've not tested, you will have the destabilization of technetium MDP and accumulation in the liver, as you can see in this picture. This is also from this reference of 2010. If you don't incubate it correctly, if you add air to the vial, or if you have too much technetium, if you've been bashing your kits. Also, antiseptic contamination with your alcohol wipe will result in some free protecnitate and low radiochemical purity. Sometimes the technetium MDP kits are also not containing the right amount of stannous chloride. I've seen this in the past. So you would get one kit out of 100 that would not label at all. So it's always important to do instant thin layer chromatography. Technetium MAA could result into clumping, so you could get focal hotspots, which is quite spectacular, and you would be able to see it. It can also lead to issues with the mean particle size, with lower biological half-life if there is smaller sizes, or if you use a too old eluate with less technetium concentration, you will have excessive number of particles that can lead to toxicity. So always remember, you have to adhere to the instructions of the volume of technetium and the concentration of the activity added, so that you don't endanger your patient by injecting too many particles. Also, if you have too large a volume of your protecnitate, even though you will only use a little bit of this for your patient, and it's all really safe, it will increase your labeling time needed to make a fully labeled technetium MAA. Technetium HMPAO, the one we all know we should be careful with. If you use the first eluate from a generator or an old eluate that has been standing longer than an hour, you have problems. If you use an old generator from like last week, then there's also issues with the balance of technetium versus stannous chloride. If you add too much pertechnetate, you will always have problems. The volume of the pertechnetate solution is an important factor. If you don't mix it well enough, but also don't shake it completely, that it's getting stuck on the vial and all of that. Radiolytic decomposition, if you add oxygen to the vial, and if your kits are not refrigerated well, all of this can have problems. And especially also then the fractionation of kits is a no-no for HMPAO. This was just an example of a patient that the first one was injected and it had a good crossing of the blood-brain barrier and no other activity. And in the second, number A was when there was some air introduced by the injection. The technician pulled up some blood and it mixed in the syringe, and then it led to some pertechnetate not crossing the blood-brain barrier. So this could be giving you false results. Then MAC3, as discussed before in depth, if you have a too small volume, it can increase hepatic excretion. There can be exposure of the kit to light can be problematic. Inadequate volume of air added during the preparation. This will lead to more stannous ions still available, and that influences the rest of the radio labeling procedure. Or if you don't start heating the product directly after you've added your pertechnetate, or if a heated product is used, so if that 15-minute cooling down period has not been adhered to, also first generator eluate or an old eluate, or if your technetium pertechnetate has been standing too long on the shelf before you label your MAC3. Problems with technetium system, maybe also the heating, the delay before heating, so you just add your technetium but you do not put it in the heating water bath immediately. Kit bashing, H eluate, exposure to air. So it comes down to the same principles all the time. So what will save today? Definitely, if you do instant thin layer chromatography, you sometimes get separation anxiety waiting for the results, especially if you had problems before. But instant thin layer chromatography will save you from problems. So if you, I cannot say enough how instant thin layer chromatography is your friend. If you have been radio labeling and your solution has been standing there on the shelf, you have nobody to ask, can you still use it? Maybe it's 4 hours after you've labeled, you're unsure. Just do another ITLC, and if it still gives you good radiochemical purity, you can still inject it into the patient. So all these questions that you normally will have in the radiopharmacy can be solved by instant thin layer chromatography. Just test it as if you just label it, and if it still gives you good radiochemical purity, you have covered all your bases and you can inject. What can go wrong with ITLC? So yeah, with every solution, there's always problems as well. And I don't want to be the bearer of negative news, but you know this for sure. So you can always look at these good practices, make sure that your sample size is not too big when you're going to scan with an ITLC scanner. If you cut your strips and you're measuring the dose calibrator, of course, your sample size should be a bit bigger. You have to have fresh mobile phase, or if you store it, don't contaminate it. Choose the right one for the radiopharmaceutical that you are using. You should not allow your strips to dry unless stated as part of the procedure. The size of the ITLC strip, you should not cut corners, cut it large enough for what you have to do. So don't make the strips too small, too thin. All of these things can save you time. And I know this is the #1 complaint, but all of these procedures, they take time, but this is to cover you as well as make sure that your patient is safe in the end. if you touch the strip at the wrong places and contaminate it with radioactivity before you run it, or inappropriate strip development and wrong measurements. I've seen people measure the strip the wrong way around or stuff like that. So please concentrate when you do your ITLC, and you can make sure that you do the right thing. So the final plugin is for Lerotu, who is doing her PhD at SMU. So she's looking at the equipment and staff availability and, in essence, the challenges that we experience in the radiopharmacy in Africa. We are very passionate about radiopharmacy in Africa and how the infrastructure, the training of personnel, as well as radiopharmacy can propel nuclear medicine in Africa forward. So if you are from an English-speaking African country and you're involved in nuclear medicine, both public and private, please find Lerotu. She's there at SASNM, and also get a link to her online questionnaire. She has a few pamphlets, and she's also sitting near the Itemba Labs booth. So please, or you can link up with her on LinkedIn for sure, and then also ask me for her contact details. I will gladly give it to you, and then you can contribute to the study, because if we don't have the necessary information to plan the future, we cannot go into the future. So this is really an important project. So the summary of good practices. Always perform QC on the first generator, eluate. Use generators that has been eluted within the last 24 hours. Avoid aged technetium eluate standing on the shelf for an hour or 2 or 5. Don't add excessive technetium activity to your kits, so no bashing of kits. Also dilute your radioactivity as early as possible after you've tested your radiochemical purity and you are pulling up doses. Avoid adding air to multi-dose vials unless it's mag-free. And then store your kits at low temperatures, but let it go back to room temperature before you label. And then I have to end my presentation. This is the lovely city of Leeuwen, where I currently find myself. I'm here till 2027. I miss you all so much. I want to also thank my mentors, Prof. Adriana Duhati and Dr. Otto Knudsen. And then this reference was really key in making this presentation happen, because there's like a load of information. And in fact, if you go to the Mexico Continued Education for Nuclear Pharmacists website, there is so much information that you can use. Then here is my email addresses. It's my personal one as well as my official work email, so you can find me on this every time or anytime, and I will answer you back. And like I said, please subscribe to my YouTube channel and ask me what lectures you would like to see. Thank you so much for your attention. Miss you all. Bye.